Hello, I'm Zach Jagone, working with Kirby McRae.
And I'm Ben Farrick, working with these other two. And this video is going to illustrate the results of a class project we did for soil remediation, spring 2017. We looked at the impact of brewer's spent grain, which is a byproduct of the brewing of beer, and how it can impact lead mobility in waste rock.
So here's a bit of background on our project. Brewer's spent grain, otherwise known as BSG, is a continuously produced byproduct of the brewing process. These spent grains are a result of the mashing process, which solubilizes malt and cereal grains to ensure adequate extraction of the solutes that drive fermentation. This process occurs on the largest scale in the production of beer, which is the fifth most consumed beverage in the world. Although the only common use of BSG is animal feed, there have been many others that have been proven to work, such as the adsorption of heavy metals from wastewater and remediation of hydrocarbon-contaminated soils. There is evidence to show that BSG is comparable to coconut husk charcoal in the adsorption of chromium, cadmium, and lead. But all of the literature discussing this only talks about its use for wastewater treatment rather than for soil, so we wanted to test if it was effective as an in-situ treatment as well. Approximately 11.4 million tons of BSG are produced right here in Montana, so it definitely has local relevance. Since much of the BSG is simply given away or sold very cheaply, it could potentially provide a low-cost solution for immobilizing heavy metals in waste rock.
So brewer's spent grain is only part of what we want to look at. Really, we're looking at waste rock and how to remediate it. Waste rock is essentially low-grade ore from hard rock mining that wasn't smelted, not really high quality enough to be worth transporting and processing. Across the state of Montana, there are 300 mine and mill sites identified as priority areas of concern by the Montana DEQ. Within all of these sites, there's a total of 502 million cubic yards of waste rock. These cover 55.1 acres, 49.5 of which are completely unvegetated. The waste rock that we obtained to do our study specifically comes from the Parrot Mine on Butte Hill, where in 1856 a 6 to 7 foot wide vein of copper ore was discovered. By 1881, the silver and copper ore production was sustainable and profitable, and by 1889 the Parrot Mine was producing 260 tons of copper and silver ore per day. What this led to was a large amount of heavy metal solutes and sediments running into Silverbow Creek near Butte. This became so bad that by 1893, a judge had ruled that the city had to change its water source, primarily due to mining activity, in part from the Parrot Mine. So remediation of waste rock is going to be essential for the continued restoration of Silverbow Creek and other streams and water bodies throughout the state that people are trying to work on improving. So, as we said before, the objective of our experiment is to see whether or not BSG additions to a heavy metal contaminated soil offer any additional benefit over other remediation treatments. So we initially started with samples of waste rock from Butte that were heavily contaminated with lead. These were pulverized and homogenized. Aliquots of this homogenized soil were given 3 different treatments. We added lime to one treatment to bring the pH from around 3 up to 6.5. We also added manure and brewer's spent grain at 5% by mass. And we also had a control with no amendments with 3 replicates of each treatment and control. So these 20-gram samples were put into 50 ml Falcon tubes. 5 milliliters of water were added to each to simulate rainfall and some sort of soil moisture. They were then uncapped the following day and allowed to dry. This whole experiment ran for about 10 days. For our analysis, we removed 3 1-gram samples from each tube, gave us a total of 36 samples. These were combined each with 20 milliliters of tapped deionized water and put on the shaker table for 1 hour. They were then left to settle overnight, and 10 milliliters of the extract was removed from the top and placed into a 15 milliliter Falcon tube. These samples were then run on an atomic absorption spectrometer to determine quantities of lead in the extract.
One important lesson that we learned is that the samples should have been filtered prior to running through the atomic absorption spectrometer. The lime and manure treatments had a significant amount of mold growing that meant they could not be run through the AA. This could be solved in the future by filtering all of the samples after they extracted so that they will not be so cloudy.
So here's what we got for hard data and results in our experiment. This plot you're seeing here is a basic scatter plot of our data broken down by treatment. The control is the group of points on the left, and the brewer spent grain treatment is the group of points on the right. And here you can already see an obvious separation between the two treatments. When we fit a simple linear regression to these points, we get an R-squared value of 0.85, which basically tells us that the treatment groups appear to be responsible for about 85% of the total variance in our data. So clearly these treatments have made a difference in regards to lead solubility.
Since we only have two groups, we can also do a simple t-test, which makes the assumption that the results are normally distributed. T-test results show an increase from 0.20 parts per million to 0.48 parts per million with a p-value of 4.9 times 10 to the negative eighth. But a t-test also makes the assumption that the sample size was suitably large. 9 samples per group isn't a lot. So at Kruskal-Wallis, one-way analysis of variation only requires a sample size of 5 per group and tests whether or not the median values of the two groups are different. This test provides a p-value of 0.0003.
Okay, so there's our results, but what else did we learn? So what we saw was substantial microbial growth in the manure and the lime treatments, which make us think they may fare better as soil amendments for heavy metal remediation. And it also makes us wonder whether or not the 5% of each of those things that we added to the soil is enough to stimulate the growth of soil microbes in the field. We also wonder whether or not that would be enough to allow plants to grow. The microbial growth was really vigorous, really robust, and was a surprise to see. As we said earlier, there's still 49.5 acres of bare waste rock here in Montana, and it seems like vegetation, healthy soil microbiome would go a long way in stabilizing that material.
So next time we'll do a better job of filtering our samples. It's too bad we weren't able to get good data from either the lime or the manure treatments. But since we've seen a large amount of microbial growth, an experiment that measures soil respiration could be very informative, as would an experiment testing the viability of plant growth in these types of soils. Ultimately, we're not ready to write off BSG as useless for soil remediation. We would like to see how further research would inform its use and subsequent study designs.
So that's our class project. Thanks for sitting and watching our video. If anybody out there on the internet has any questions about what we've done, would like to know more, you can get in touch with us at these email addresses you should be seeing on your screen. Thanks a lot.